Okay, so I wanted to look at a little bit of 2.5. I'll try to keep this relatively brief. It shouldn't be more than about a 5-minute video. I rigged up a little question here to kind of help just solidify some concepts here. I've got this nice little polynomial. It's a 3x to the fourth, 28x cubed. You got it all there. You'll notice x to the fourth, third, second, first, constant. There's no missing coefficients. I almost wish there was a missing coefficient, but it's all good. And I gave you a little note down here that -3 plus I is one of the roots, and we're going to find all of those remaining roots, okay, whatever they happen to be. Now, I do want to remind you that in 2.5, we discussed the fact that if this is a fourth degree problem, there are exactly 4 roots to be found, and we want to find all 4. Now, we also have this thing called the conjugate roots theorem. So as soon as on a test I were to tell you, say, that -3 plus I is a root, automatically you're going to know that -3 minus I is necessarily also going to be a root. So I gave you some options on how to divide those things out. But before I do, I wanted to remind you a little bit of Descartes' rule of signs. Now, these are both imaginary roots. They're not real, okay? But Descartes only was interested in the real when he first started this thing, and he looked at this and said, hey, this first coefficient is positive. It stayed positive, it stayed positive, it stayed positive, but it moved to negative right here. So he saw exactly one sign change. So he said that there would be one real positive root. So when we look at this, I have 2 imaginary roots, and there is a positive real root for sure. That means the remaining root is probably going to be then negative. So what he did is he said, let's look at f of negative x. Because if we do f of negative x, it takes the graph and it flips it over across the y-axis, and it takes everything that used to be negative and makes it look like it was positive. But if I did f of negative x, 4 negatives would make a positive. 3 negatives would make a negative times a positive. 2 negatives times a positive is positive. A negative times a positive is a negative, and it stays negative. And notice that I had 1, 2, 3 sign changes. So Descartes knew there was either 3 or 1 real negative root. But we actually know better, because there could not be 3 reals and 1 real for 4 because we had 2 imaginary. So we know there's going to be one of these and one of these, and we're ultimately going to figure out what those 2 real roots are in a moment. But the nice thing is, we're going to go at this thing and just use what we know to be true. I know that -3 plus I is in fact a root. So I'm going to do synthetic division, because I was guaranteed in the question that if I divide these things out, they will in fact divide out perfectly and have no remainder. So what we did in class is we said, let's take this root that we have, which is -3 plus I, and we said, let's go ahead and store that as alpha A. So now remember, the store button is down here at the bottom. That's store. We hit the green button, and then we tell it what letter we want. We could use A, B, or C, any letter. I just usually choose A because it's easier. So in my math, I'm going to drop the 3. I'm going to see if I can make this fit here. I'm going to take 3 times A, and I've got -9 plus 3I. I'm going to add 28 to that, because in synthetic division we simply add. Multiply again. I've got -60 plus 10I. Add that to 82. That's 22 plus 10I. Multiply by A again. -76 minus 8I. Add it to 52. I'm starting to get nervous that this is actually working. And I got it. Wow, I didn't think it was going to work. Now notice it says 80 plus no I, so I didn't bother. So it confirmed what I knew to be true. Now, what's supposed to happen by promise is all of these imaginaries should cancel out. But again, we haven't finished, because we know we divided this one out, but we need to divide the other imaginary or complex root out. So 3 times this would be negative 9 minus 3i. Add down gives me 10. Now, incidentally, we had a fourth degree, and by the time we're done, we've divided out 2 roots. So that should leave us with exactly a second degree equation. So this would give me negative 3 times 10 is negative 30. Negative I times 10 is minus 10i. Then I add those down, I get negative 8. And then over here, negative 3 times 8, negative 8 is 24. And that's plus 8i. And what do you know, it worked. Now keep in mind, I said this was going to be a quadratic. So we had 3x squared, we had 10x's, and we had minus 8. And hopefully we can factor this. So depending on how we like to do this, I think a 3x and an x is pretty good way to start trying to factor. Now again, I didn't guarantee that these 2 roots that we talked about would be rational. I might have to go with the quadratic formula, but hopefully I can factor it and get nice numbers. So I think this should work. And 8 is a pretty nice one. It's either 8 and 1, but most likely 4 and 2. So if I had 12 x's and 2 x's, I could certainly make 12 and 2 into 10 if this was positive and that was negative, and that would make that negative 8. So my 4 roots that fit what we have were negative 3 plus and minus I, that's 2 of them. We also had a root at x equals negative 4 and another root at x equals 2/3. And that would be all of those roots. And of course, if we wanted to take it one step further and write it as a product of linear and irreducible quadratic factors, we could say that my original function f of x had a 3x minus 2, which is a linear factor, x plus 4, which is another linear factor, and we had our special way that we looked at these, x squared. When we add them together, I got negative 6, so I'm going to go plus 6x, and negative 3 squared is 9, 1 squared is 1, 9 and 1 make 10. And in fact, that is exactly what I typed into a program to generate the polynomial that I used to make this video. And so that is actually kind of the end of our story for this one. But if you really wanted to, we could have avoided the synthetic division by taking x squared plus 6x plus 10 and dividing it into the original polynomial, which I don't think I'm going to bother to do in this particular story or this video. But if you did that, you're going to see that x squared times something gives me this, which is 3x squared, which is shouldn't be surprising. When we look for the next piece, we're going to find out the next piece that would be necessary would in fact be the 10x like we had before and minus 8. They're going to give us that same information. Some people like this one better because it just took exactly 3 steps in this division to work. This one up here really took more than 3 steps, but it's all good. There's different ways to approach this, but this has just been a short video on some information regarding 2.5. And again, I'll see you back in class.